Section 11. I've only got about 45 minutes right now, so this one is going to be divided into two recordings, but I figured I might as well get some of it taken care of anyhow. This week, we look at the mechanics of fluids, which the word fluid I'm using in the most general sense here. Sometimes people hear the word fluid and they assume you're talking about liquids. Here it means anything that will flow, a liquid or a gas. Although actually, when we get into the specific equations that we're using, they actually would only be exactly true for liquids. But well, we'll get to that in a moment. Some terminology, first of all. One thing that you sometimes find yourself needing to talk about is the density of a liquid. The usual symbol for density is the Greek letter rho, like it says over there. I know it looks a little bit like a P. It's actually a Greek R, not a Greek P. Try and make it look a little different from P, because before we get to the bottom of the page, there will be an equation that has P for pressure and rho for density in the same equation. And you know, not good to mix them up with each other. Anyhow, density is the mass per unit volume. Stone is denser than wood, that kind of thing. In a given amount of volume, more mass is present in a piece of stone than in a piece of wood. Pressure, sometimes what matters is not the total amount of force acting on something, but rather how concentrated that force is, how the force is distributed. Just a second. I was fumbling around trying to find this photograph that I clipped a few years ago. So we've got somebody standing in a pair of mismatched shoes. It would be kind of nice if it focused better than that. And presumably the person is not leaning to one side or the other, so that there's more or less equal amounts of force bearing down on the heels of both shoes. But notice the difference in what happens to this rubber mat this person is standing on. Here, you have a smaller amount of pressure because the force is distributed over a larger area. Here, on the other hand, with the same force distributed over a much smaller area, it creates a much greater amount of pressure and squishes the rubber mat a lot more. So same force, different amounts of pressure. Sometimes what matters is how the force is distributed, concentrated or spread out. And that's the idea behind pressure. In traditional units, pressure would be measured in pounds per square inch. The metric counterpart would be newtons per square meter, force in newtons, area in square meters. This combination of units is given a name of its own. It's called a Pascal. A Pascal is quite a small amount of pressure compared to a pound per square inch. So quite often you'll see pressures described in kilopascals. Like if you look at the tires on a car, somewhere in all that fine print that they've got stamped on the side of the tire, it has the maximum pressure that the tire is supposed to be inflated to. A typical car tire might be 44 pounds per square inch. And you'll see in parentheses after that, 300 kPa, and the kPa stands for kilopascals. So that's, you know, it's easier to say 300 than 300,000, but if you're going to do any kind of calculation, It's pascals, not kilopascals, which would be the SI unit that you need to mesh with the other units around it. The difference between absolute and gauge pressure. Well, let's continue talking about tires for a moment. Let's say you're driving down the road one night and you don't notice until it's too late that somebody has. I was driving into work it was quite a few years ago actually, but there was some guy going down the road ahead of me in a pickup truck, and he had the tailgate down on the pickup truck, and he had a cardboard box of nails. You know where this story is going, right? He goes over a bump, and the box of nails spills out of all over the road, and well, I was able to go around it anyhow. But so yeah, let's say you didn't happen to swerve in time and ended up with about 50 nails in your tire, and so you pull over, and the rim is right down on the ground, but not having anything better to do while you stand around waiting for help, you put a tire gauge on there, and somebody who has a tire gauge with them probably doesn't need to stand around and wait for help actually. But if you put you put a gauge on this tire, it reads 0, right? But think about it. There is no way that a tire with 50 nails in it is going to hold a vacuum. The pressure inside that tire is not 0. The pressure inside that tire, standard atmospheric pressure, is 14.7 pounds per square inch. It's usually a little lower than that at this altitude because we're 900 feet above sea level here. So something that rounds off to about 14 pounds per square inch is what you've got inside that tire, but the gauge doesn't say 14, it says 0, because what most pressure gauges read is not actually pressure, it's differences in pressure. If the gauge says 30 pounds per square inch, that means that the pressure inside the tire is 30 psi more than what you have on the outside. Okay, if there's 14 outside, standard atmosphere, or typical atmospheric pressure, then if the gauge says 30, what you've really got inside is 44. So that's the difference. Absolute pressure counts all the pressure that's there, the total pressure relative to a vacuum. Gauge pressure is what a pressure gauge reads. That's how far you are above or potentially below atmospheric. Gauge pressures can be negative if you have a pressure below atmospheric. Absolute pressure cannot, because how do you have less pressure than a vacuum? The way to convert from one to the other would be to add or subtract atmospheric pressure. Generally, when people talk about pressure, they mean gauge pressure, like the writing on the side of a tire when it says that you should have however many pounds per square inch. It varies between different tires, but for the maximum safe pressure, that's giving you the gauge pressure. That's telling you what your gauge should read. But for purposes of a course like this one, the word pressure usually means the absolute. If I mean gauge pressure, I'll say so, or something equivalent, like the question will say, well, there's a pressure gauge and it reads blah, blah, blah. Okay. If it says something like that, it's gauge pressure. If I just say pressure, it's the absolute. And you can get the place you can look up atmospheric pressure, which is what you need to convert from one to the other. Actually, I've got the formula sheet here somewhere, don't I? Right on the last page, there's the table of units. And if you go down to last thing on the bottom, where it says pressure, you can see over here in the conversions column that 101,000 pascals is standard atmospheric pressure. That means an average day at sea level. Atmospheric pressure varies with the weather and with altitude. I mean, 900 feet above sea level is not exactly sitting on a mountaintop, but even here at Batavia, I have never seen, because there's a barometer up in the chemistry lab. I have to read once or twice a semester because we need the number for some lab we're doing down here. And I have never, ever seen atmospheric pressure that high. It's usually around 98 or 99 kilopascals rather than 101 at even this fairly modest altitude that we have here. Okay, so I'm going to run through an example that illustrates the idea of pressure, and then we'll talk a little about hydrodynamics. So I think this actually was the dimensions of I think I actually measured up one of the windows in my office, and we're assuming standard atmospheric pressure, even though it's not quite realistic for here. Let's figure out what the pressure on that, or the total force on that window would be. This is just a matter of saying, you know, if pressure is force per unit area, P equals F over A, well, you can look up the atmospheric pressure, and the area of the window is given. So you know 2 out of the 3 things in the equation, P equals F over A, and you can solve for the third one. The trick is the units, okay? A Pascal is a Newton per square meter, but you were given an area in square centimeters, and there's a little trick involved in that. P equals F over A, follows from that F equals P times A. Multiply both sides by the area. Since the question says nothing to the contrary, we'll assume standard atmospheric pressure. What other choice do we have? .01, if you want to go a little further with it, 1.013 times 10 to the 5th pascals, newtons per square meter, in other words, for the atmospheric pressure from the place on the formula sheet that I just showed you. The area, 16,800 square centimeters. But notice, square centimeters does not cancel with square meters. You need to convert. Well, here's where it gets tricky. A lot of people realize that they need to convert so that the units match, but they do it by moving the decimal 2 places, and it should be 4. 1 meter equals 100 centimeters, but centimeters to the first power does not cancel with centimeters to the second power. You have to do that. There are 100 linear centimeters in a linear meter, but there are 10,000 square centimeters in a square meter, okay? if you don't like an algebraic explanation of that, like I just went through here, we can go geometric instead. I can draw a picture. A square meter, I'm kind of estimating here, but a square meter is probably about that big. A square centimeter is about that big. I'm not going to draw them all, but there's 100 of those little guys in just the first row. Okay. By the time you fill a square that's 100 by 100 centimeters, there's 10,000 of them. So to convert square centimeters to square meters, you have to move the decimal 4 places, not 2. And of course, it works the same, in traditional units. There's 144 square inches in a square foot. Nine square feet in a square yard, and so on. So back over here. If you move the decimal 4 places, well, that would be there, I guess, 1.68 square meters times this, and you've got 1.70 times 10 to the 5th newtons, which in somewhat more meaningful terms is about 19 tons. So you have this delicate piece of glass with 19 tons pushing at it on the one side and 19 tons pushing on it from the other side, perfectly evenly distributed all over both sides. So it creates a state of balance and nothing happens to the window. But if I tried pump, this would be kind of difficult because it's not really a very tight enclosure. But if I were somehow able to pump all the air out of my office, the window would not last long. Okay, 19 tons on one side of it, nothing on the other side of it. There'd just be little pieces of glass everywhere. Okay, pressure, force per unit area. And now, most textbooks actually do hydrostatics at the front of the chapter and hydrodynamics toward the back, but I kind of like to do it the other way around just because once you have the equations for a flowing fluid, then you can move on to the static case by just setting the speed of the fluid equal to 0, which seems kind of efficient to me somehow. But, the words mean the same thing they do in general, statics and dynamics. Statics is the study of objects remaining at rest, and dynamics is when you've got things moving around. So let's say you have a pipe and there's some sort of, maybe water flowing through it, or it could be compressed air. Like I said, I'm using the word fluid to mean anything that'll flow. We want to compare what's going on at one point in this pipe to what's going on somewhere else in this pipe. Point number 1 and point number 2. These 2 points might differ, first of all, in elevation, H1 and H2. They might differ in the cross-sectional area of the, well, like if this was a 1/2 inch pipe here, and this is a 1 inch pipe over here, the numbers, when you talk about it like that, the numbers refer to the diameter of the pipe. If this is a 1/2 inch pipe and this is a 1 inch pipe, then A2 would be 4 times A1 because, area, pi r squared. You double the radius and you got 4 times the cross-sectional area. And the 2 points might differ in pressure, P1 and P2, They might differ in how fast the fluid is moving. V here for velocity, V1 here, V2 there. Now, we are going to restrict ourselves to a special case, okay? We're trying, this is just an introductory kind of a survey course where you spend a week looking at this and a week looking at that. And like many of the things that we spend a week looking at in this course, you can take an entire course on this stuff, okay? It's typically required for mechanical engineers, for example. In the 3rd or 4th year, they have to take a course on fluid mechanics, okay? And so you can get a lot further into it than the little bit of scratching the surface we're going to do here. We're going to look at a special case and leave it at that. So smooth, meaning that, well, it means streamlined flow. Okay, there's no turbulence. Turbulence is a very complicated subject, still very much a topic of current research, whereas smooth, streamlined flow has been well understood for close to 300 years. Steady just means that it's not changing with time. Some little kid over here is not turning the faucet on and turning the faucet off and turning the faucet on and turning the faucet off. It just, time passes, things don't change. Without internal friction, the fluid has no viscosity. That is kind of unrealistic, but it's a decent approximation as long as you don't have a really narrow tube or you don't try and make it flow too fast. An incompressible fluid means that as you apply more pressure, it does not get smaller. That kind of restricts us to talking about a liquid. Gases are very compressible. You get a balloon full of air and you squeeze it between your hands and it gets smaller. If you have a water balloon and try and squeeze it between your hands, it does not get smaller by any meaningful amount. So these two equations that are just below the picture here, they only apply exactly to liquids, not non-turbulent flow of liquids without much viscosity. But if you want to talk about compressed air going through a pipe, you get the same general sort of behavior. If you want to just talk about it qualitatively, the fluid still does the same thing. It's just some of the details are a little different. The equation of continuity, for example, if it's a gas, it becomes A times V times rho equals a constant. Okay, so things get a little more complicated if it's a gas, but you get a lot of the same general behaviors. So the equation of continuity basically says that where the tube gets smaller, the speed gets bigger. Common experience, if you've ever had water flowing out of a garden hose, okay, you're standing in the backyard watering the plants. And for whatever reason, you want to squirt some water over there, 5 or 10 feet away from where you are. You put your thumb over the end of the hose, right? And what happens is with the end of the hose wide open, the water just kind of falls out and lands not far from where you're standing. But you put your thumb over the hose and the water squirts through there real fast and goes way over there instead. So when the cross-sectional area goes down, the speed that the water shoots through there goes up. And that's kind of what the equation of continuity is all about. If you pick 2 points like here and here, A times V at the one point is equal to the same thing you would get from A times V at the other point. A is the cross-sectional area, V is the speed of the fluid. And I got to boost this up a little if you're going to see the Lewis equation. there was a whole family of Bernoullis back in the early 1700s. Somebody once said that the Bernoullis were to mathematics what the Bachs were to, because, you know, Johann Sebastian Bach, he had like a bazillion children, several of which became fairly decent composers in their own right. And the Bernoulli family in Switzerland was the same kind of thing. I don't know how the Bachs got along with each other, but the Bernoullis didn't really like each other very much. But, well, if you're interested in that kind of thing, look it up. I always kind of liked history because, you know, it's a story. And unlike some piece of fiction, somebody makes, you know, you read a book and you go, real people would never do that. Yeah, when it's somebody's biography, they would actually. But once again, it's a matter of some quantity that if you calculate it at the one point, you're going to get the same thing as if you calculate it at this other point here. And it's a little more complicated than just A times V. It's the pressure plus 1/2 rho V squared, where, oh, there goes the focus. Rho is the density, V is the speed. Over here, rho is once again the density, G for gravity, 9.8, H for height, as shown on the diagram. Bernoulli's equation, if you go through how to derive it, it comes from the work energy theorem, okay, which you can see kind of what's going on here. 1/2 rho V squared, that's the kinetic energy term, kinetic energy per unit volume, because we have here the mass per unit volume, and rho GH, that would be the potential energy term, potential energy per unit volume. So, well, let's run through an example that makes use of this. You've got a tube, which actually looks a lot like this one here. I'll get back to that in a couple of minutes, but it's got a narrow spot here. And in this example, there's water going through the tube, and over here it shoots out into the atmosphere. Well, once the water gets into the atmosphere, it's going to be, not too surprisingly, at atmospheric. Oh, wait a minute. I'm below the bottom of what you can see. Got to readjust this again. Everybody's sitting out there going, I don't see any picture. What's this guy talking about? Okay. Example. Very fuzzy example. Focus. Okay. Where the water shoots out into the atmosphere, it's at atmospheric pressure. Yeah, 1.01 times 10 to the 5th is standard atmospheric pressure, but maybe today a low pressure system is going through. I just thought it would be kind of nice to have a nice even number. Gives the cross-sectional area of the tube, both here and here. It gives the speed the water shoots out into the air. We're supposed to figure out what is the pressure in the water here. Now, pressure is in Bernoulli's equation. So we're going to have to get our answer out of this equation here. But the little problem we need to take care of along the way is that it also involves the speed. In order to be able to solve for P, we need to know everything else in the equation. So step one, I got to figure out how fast the water is moving through that neck there. I can get that out of the equation of continuity. So step one, get V out of this. Once I know that, put it in there, solve for P. That's the strategy. That's the plan of attack. Details look like this. This is another one of those things where I'll do a problem and then you'll do a problem. Yeah, that seemed about where I want it. So here's a sketch of that tube again. I just wanted to label that what I mean by point number one is the place where we're trying to figure out the pressure. And point number two is over here where the water shoots out into the atmosphere. So A1 equals A2 V2, equation of continuity. We're after V1. When in doubt, convert to standard units. It's not always necessary, but it's never wrong. We were given these areas in square inches, but the speed in meters per second. So you might be sitting out there going, oh my gosh, we can't have that. We're mixing two different systems of measurement. Yeah, well, like I said, when in doubt, convert to standard units, which would be square meters for the area. But if you keep an eye on the units, sometimes you get away with shortcuts. This is one of those times. The area over here at point number 2 is 1 square inch. The cross-sectional area of the tube here is 1/3 of a square inch. And the speed over there at point number 2 is 3 meters per second. So the thing to notice here is if I leave it in square inches, don't go to the trouble of converting to square meters, units cancel each other anyhow. So converting to square meters would just be wasted time. It won't give you the wrong answer. It's okay. So when in doubt, convert to the standard unit. But if you keep an eye on things, it's like, oh, well, you know, all that matters is the ratio. It's a 3-to-1 ratio, no matter what units I measure things in. So anyhow, dividing by 1/3 is the same thing as multiplying by 3. And so this comes out (9 meters per second). So the underlying idea behind this equation is that where things get tight, the fluid speeds up, okay? You put your thumb over the end of the garden hose and that makes the water squirt through really fast. Now that we know that, we can go to Bernoulli's equation. P plus 1/2 rho v squared plus rho gh is a constant. In other words, if you write that quantity down for point number 1, it's equal to what you get if you write it down for point number 2. In this particular case, the potential energy terms drop out because it's a horizontal tube. H2 is equal to H1. So probably the sensible thing to do is to say that's the level you're going to call H equals 0. I'm going to measure my heights from here. which makes that 0 and that 0. But even if you measure the heights from somewhere else, that is still equal to that. And if you subtract it from both sides, it's gone. So because H1 equals H2, the potential energy terms are not a factor in this particular problem. Filling numbers into the rest of it, we've got P1, it's 1/2 rho for density, and the fluid that this particular question is about is water. The density of water is, here, just a second, formula sheet right here. Now, some of you may have kind of memorized for some other course that the density of water is 1. It's 1 gram per cubic centimeter. In this course, we don't usually measure things in grams per cubic centimeter. We measure in kilograms per cubic meter. So this is page, if it'll focus on it, that's page 5 of the formula sheet. And you go down here to where it says some physical properties. And second from the top there, it says density of water, 1,000 kilograms per cubic meter. So that's what we put in for rho. Go sticking grams per cubic centimeter in there, and there will be a decimal error. Just got done figuring out that the speed of the water is 9 meters per second at point number 1. Over at point number 2, the pressure is given on the picture that came with the question. You've got 100,000 pascals there, 1.00 times 10 to the 5th. And I'm starting to run out of space. Better put the rest of it down here. 1/2 rho v squared over on the right. Same density, but over here, the water is only going 3 meters per second. And a little bit of number crunching now. May or may not want to bother putting down all these details in your notes, but I find that if I don't write out a lot of detail up here on the blackboard, there's always people kind of look, if I just jump right straight to the answer, people go, hey, what, how did he get that? So too much detail is probably better than too little for this kind of thing. So you add that to that and then subtract this, and the pressure comes out 6.4 pascals. The thing I want you to notice about that, well, aside from, how to use the equations, the other thing I want you to notice is that that is less than atmospheric pressure. It's less than 2/3 of atmospheric pressure, actually. So if this tube springs a leak right there, water doesn't squirt out. Air gets sucked in, okay? This seems to be rather counterintuitive. A lot of people just seem to think it's common sense that if you've got a tight spot like that, that the pressure would go up there. But this is not the case. Actually, let me pause it for a second and get something set up. I'm going to do a little demonstration rather than believing all these calculations. We're going to go with the seeing is believing. Okay, so I have here my glass tube shaped just like what we were talking about. And what I'm going to do is I'm going to blow through it. Okay, this is going to be air flowing through the tube rather than water, like in the example I just ran through. But as I said earlier, the same basic principles apply, just a few of the details are a little different if it's a compressible fluid instead of an incompressible fluid. But these two little things here are blocked off. Got a little bit of clay I stuck in each one to seal it, but what this tube on the one in the middle is for is to make sort of like a pressure gauge kind of thing. I'm going to stick that in this beaker of water. And if in the narrow part here, if this sort of thing is called a Venturi tube, by the way, if anybody's interested in jargon, but if I create high pressure there, the way some people seem to feel ought to be the case, well, if I blow hard enough, I'll make bubbles. You know, the water level would go down the tube and it should make bubbles in the water, right? But when I actually try it, here's what happens. I don't know how well that came through. Let me show you that again. Yeah, I think you could see that. I think I saw it on the monitor over there. Hopefully what you saw was a lot of little droplets of water shooting out the end of this thing. One more time, just because I'm right here and it doesn't take long. So because of the low pressure created here, the water gets drawn up into the airstream where it breaks up into a lot of little droplets that go blowing out over here. There are quite a few applications for this kind of thing, actually. For one thing, this is basically a carburetor. Actually, this is a carburetor. This is off of a lawnmower that I had a number of years ago, and eventually the thing got all rusted out and couldn't really use it anymore, but I kind of brought some of the parts of it to, you know, it donated its body to science. So if you kind of take I've got to hold this at the right angle. Open up the throttle to let a little light through, and you can see that in the middle of it there, it gets a lot narrower, okay? Just like that glass tube I was blowing through. And actually, maybe you can see sticking up out of the bottom is a little short tube, about the same diameter as the lead out of a pencil, just a little, but where that goes, that tube goes down to the bowl in the bottom here. This bowl has gasoline in it. And the gasoline gets sucked up that little tube, just like this water gets sucked up this tube here. And that's how you get your air fuel mixture, okay? As the draft goes into the engine, you know, the piston goes down the cylinder, it draws in a lot of air behind it, which makes air flow through the carburetor. And so as the air goes blowing through the carburetor, it creates the same kind of suction you just saw with this thing here. The gasoline is drawn up into the airstream where it separates into little droplets, kind of like are all over the counter of the, see, I kind of made a mess out of the desktop here. Those little droplets evaporate pretty quickly because, you know, they're small, and that's how you get your air fuel mixture. Cars have not used carburetors since the 1980s. An automotive carburetor is quite a bit more complicated than this one, but carburetors are still used quite often on small engines, lawnmowers, chainsaws, things like that. And that's, well, another device that's practically the same thing as a paint sprayer, okay? You hook it up to your air compressor so that air goes blowing through the tube, and you've got a can that's full of paint rather than gasoline. Same sort of thing. The paint gets sucked up into the airstream and you blow it all over the thing you're trying to paint. The air does not have to necessarily be confined inside of a tube either. It can just be out in the open, and the same principle applies. That principle being that, let's go back to Bernoulli's equation for a second here. You've got pressure here. I should probably just write it down. Pressure plus 1/2 rho v squared is constant, assuming, there's no significant difference in height, which even in an automotive carburetor where where the air flows down vertically instead of horizontally, how much of a difference in height is there between the top and bottom of a carburetor, really? So where there's no significant difference in height, well, think about how this would work. In order to still work out to the same constant, if this gets bigger, this has to get smaller, okay? So if the speed goes up, the dynamic pressure goes down. So you've got a trade-off there between speed and pressure. And then the other fact, as far as Bernoulli's equation in words, rather than just throwing numbers at formulas, you've got this trade-off between speed and pressure. That's the one thing that's going on. The other thing is, if there is a significant difference in height, the farther down you go, the greater the pressure becomes, which is something any scuba diver can tell you. You start diving down into the ocean, and the farther down you go, the more water is sitting on top of you. That water weighs something. So at greater depths, you get greater pressure. So that's what's going on behind all the Greek symbols and things here, is a trade-off between pressure and speed, together with the fact that the pressure increases the farther down you go. So I was saying how that works even if you're out in the open. This is one of the factors that's responsible for the pressure or for the lift on an airplane wing. You've got, seen in cross section, an airfoil looks something kind of sort of like that. And the air flowing past it does something kind of like this. Of course, I'm taking what's actually a very complicated story and simplifying it down, but the wing is shaped in such a way that the air going over the top of the wing has to cover a longer distance to get to the back edge compared to the air that flows under the bottom of it. To cover that greater distance in the same time, it has to go faster than this air down here, where the speed is higher, the pressure is lower. And so you have a difference in pressure between the top and bottom of the wing, which creates an upward force, which is part of what supports the airplane. There are other things going on also. So that's the last couple things at the bottom of the page there, where speed is higher, pressure is lower, and I mentioned some examples. So now it is time for you to try your hand at some of this. I have number one is a conceptual type question with no specific numbers in it. Number two is kind of like the one that I just went through, except this time there's a significant difference in height, so that part of it won't drop out. I want you to work on both of those, but this time I'm not going to tell you to pause the video. Rather, here's where I am out of time and I need to go do something else. So if you want to see me go through these two problems, that will be the first thing at the very beginning of the next video. So just end this video once you got all the information off this that you need to, just end this video and go back into Blackboard, drop down one notch, start the next one.